All right. Let's talk about geo-distributed applications and see how to build those by using the global cloud infrastructure. In this session, we are going to talk about high-level architectural design patterns and consideration. This session is not tailored to any specific programming language. Instead, we will see how to build those applications, how to design the data layer, how to arrange our microservices and the other parts of the application stack. But then, when it comes to the development, it will be up to you. You will decide how to take these design patterns and considerations and implement with your favorite programming language. All right? So, speaking about their agenda, we will walk through 3 steps. Step number 1. We need to remind ourselves of the global cloud infrastructure that is provided by major cloud vendors. We are going to talk about different resources, about regions and zones. After that, we will do an introduction to geo-distributed applications. How those applications are different from standard applications, what are the benefits, what are the trade-offs. And eventually, with step number 3, we will practice in designing and architecting a geo-distributed application by taking a Slack-like corporate messenger as an example. Okay? So the global cloud infrastructure. When it comes to the infrastructure, you know that every cloud provides various resources. We have virtual machines, we have network, we have disks and other types of hardware. And those resources are grouped and located within regions. A region is an independent geographic location, such as US West 1, Europe West 2. On this map, we have regions in North America, in South America, Africa, and other continents. When it comes to their speed and latency within a region, all the resources of a single region are interconnected through a high-performance network. But what if you need to send, let's say, requests from one region to another region? The latency will vary. The latency will depend on how far each regions are located from each other. If to take Google Compute Platform as an example, then the numbers are as follows. Let's say that we have an instance of application running in Oregon, US West, and we want to send the request and get an acknowledgement or response from North Virginia. The average round trip is around 60 milliseconds, pretty fast, right, across the country. But if the same application from Oregon needs to send the request to London, the latency will double. It will be around 130 milliseconds. The latency will be even worse if our application from Oregon needs to go to Mumbai in India. The latency will be around 220 milliseconds. But at the same time, if your application needs to go to Tokyo through the Pacific, somewhere here, then the latency will be 90 milliseconds, much faster than a request and response to and from Mumbai. So what a conclusion can we make? All the regions are interconnected through different networking channels. Some of the channels are faster, some of the channels are slower. That's why when we will be talking about geo-distributed applications, the components of those applications, such as the data layer, application layer, microservices, will span across the globe. And you need to be careful about when you pick specific remote regions, because you have various regions and the connectivity between those regions varies. Or you need just to apply different patterns that we are going to discuss. Going from the regions, every region consists of zones. And zone is a separate physical location within a region. So on this map, we have approximate boundaries of the US West 1. We have 3 zones in this region. And usually you have 3 or more zones for the high availability needs. If you, let's say, deploy your application, your solution in across 3 zones, like instance of the application such as Nginx web server is running in zone 1, zone 2, and zone 3, then you can withstand zone level outages. If this zone goes down, your application web server is still running because it's running in other zones. That's why we have zones. The latency between the zones is extremely low. All the resources within the zones are interconnected through a high-performance network. If to refer to Google Cloud Platform again and to talk about Google's infrastructure, then the round-trip network latency is under 5 milliseconds on the 95th percentile, and that's extremely fast. It's just the round trip between the zones. And finally, we have regions. Every resources within a region are scattered across the zones, but also many cloud providers expand their infrastructure to densely populated metropolitan areas. And they have services or like products named as local zones or local edges or edge nodes. What's the purpose of those local zones? They are usually required for applications that are looking for single-digit millisecond latency for their end users. The best example here is gaming applications or streaming applications. So if you have a lot of the users who live in Seattle, Atlanta, London, or New York, you want them just to consume, to use your service the fastest way possible. And you want to store the data, you want to run instances of your microservices the closest way possible. That's what those local zones are designed for. Anyway, as you see, the global cloud infrastructure is really broad. And with that infrastructure, we as architects can design and build applications that have several characteristics. First, your global or geo-distributed applications can provide similar performance and experience to your end users without, regardless of the user's whereabouts. So let's say that you have an application, and originally this application was launched and used by your customers from Europe, but right now it's gaining popularity in Asia, and you want your users from Asia to have the same level of experience as your European users have. And with the global cloud infrastructure, it's extremely easy to do this. If your application, your data layer, your application layer spans and also exists, has a representation in your Asian data center. Okay. The second benefit of the global cloud infrastructure that we can take advantage of is we can comply with data residency requirements. Let's take another approach. Let's say that you launch an application primarily for APAC, Asian market, but right now you see that citizens from Europe kind of looking at it. You see a lot of the demand from Europe. And if you want to launch and expand this application to Europe, it's highly likely that you have to comply with the local requirements, such as GDPR. And again, the cloud infrastructure allows us to do that, right? You can have, let's say, you can keep the data of your application in the European data centers, and you can deploy instances of your microservice. The only topic that is left is how to architect such a geo-distributed application. And finally, with this architecture, you can tolerate cloud failures. For instance, what if, let's say, you have US West and you have a region in US West and you have a region in US South. If the region is US West goes down, your traffic for North American users can redirect it to another region. It's possible to do. It's all about how to implement it at the application and data layer. The infrastructure exists. Having said that, let's do a quick introduction to the geo-distributed applications. A geo-distributed application is the application that spans across multiple geographic locations. For what reasons? For high availability, compliance, and performance needs. On this picture, we will start talking about our geo-distributed corporate messenger. And this picture shows that our messenger instances and components of this solution run across the globe. We have North America, South America, Asia, and other locations. Okay? But let's quickly step back. and review what are the downsides of standard applications. The applications that are usually deployed and run in a single availability zone of your cloud environment. On this picture, we have the same corporate messenger, but it's deployed in one of the regions and it's deployed in one of the availability zones. That's a default actually deployment mode and configuration for most of the applications. And what happens? What are the downsides? If the zone goes down, so does your application. Your application, your messenger becomes unavailable. Your users will be disappointed, at least disappointed. Some of them will never return if the outage takes a lot of time to recover from. Other downsides that you can, or roadblocks that you can experience later. Let's say that initially this application messenger was designed for your North American market, and their startup founders told you, hey, no worries, we're just going to build and break and disrupt, but let's do this incrementally. Let's kind of build this application and deploy it and test it with our North American users. But then, like, what happens in, let's say, in half a year, the plans are changed and you suddenly have to expand this application to Europe, right? How are you going to comply with the local data residency requirements? How much effort and time should you put in redesigning your architecture? Okay, so that's the problem with single zone applications in data layers. And final one is user experience. Again, the same application, but then let's say in a year and a half, you decided to expand to Asian market, to Japan, to Singapore, right, to India. So, and you want those users from those locations to have the same level of experience, the same speed and the same scale. But if those users from Japan or India needs to send, the applications need to send requests to your data center in Europe or in America, then the experience will not be the same, it will be poor, okay? So that's what geo-distributed applications are dealing with. And when it comes to geo-distributed apps, there are two primary deployment modes, right? When we are talking about geo-distributed apps, we want them they have to be resilient and withstand various cloud outages. They have to be performant, even if you deploy them across multiple zones or regions, and they have to comply with data residency requirements if necessary. So let's quickly review multi-zone type of deployment, because the multi-region one we will review in detail while designing the Slack-like corporate messenger. So on this picture we have the same messenger application, but right now it's deployed within the same region but across multiple availability zones. You have, let's say, instances and data layer in zone 1, zone 2, and zone 3. So what are the advantages and disadvantages? So from the resiliency standpoint, such architecture is much better than a single zone deployment, because if any of these zones goes down, the other zones are live and you are happy, right? And your customers and users are happy. So this configuration can withstand, tolerate zone level outages. From the performance standpoint, remember, if to speak for the Google Cloud Platform, a round trip is under 5 milliseconds. So the communication, if you have the data layer here, the communication, you need to replicate changes, you need to keep copy for the same message across multiple zones, it's fast. It's like extremely fast. From the data residency requirements, the thing is not that trivial. I mean, if it depends on where your region is. If your region is in North America and then in half a year you need to expand your messenger to Europe, then it's going to be a little bit complicated, because this solution is in North America, but you need to keep data of your European users in the European data centers. That's where the multi-region deployments come into play. With multi-region deployments, from the resiliency standpoint, you can tolerate region-level outages. If, let's say, your US West Coast region is completely down, then your users can be directed and read and write messages to, let's say, Midwest regions. From the performance standpoint, as long as your deployment spans multiple regions, on average, it will be the performance will be lower if to compare to multi-zone deployments, and latencies will be higher. But with multi-region deployments, there are multiple deployment options, and we are going to review those a little bit later. Just fasten your seatbelts and wait. So it's not, that standard. And from the data residency requirement, we are good. I mean, if you deploy across multiple regions, if one day you need to scale to Europe or to Asia, you can easily do that, right? So now let's architect that Slack-like corporate messenger. To remind you, most likely, I believe that most of you have heard about Slack or use this messenger daily. With that messenger, your company, your employer creates a workspace, you create channels, and you communicate and chat and talk with your colleagues. Also, like many communities, open source communities or other communities, use Slack for conversation between their members. And Slack, believe me or not, actually is a geo-distributed application. So if you check this engineering blog by the Slack team, you'll see how, like, their story, eventually they started as their, let's say, standard application with MySQL, but then they scaled, they turned their architecture into a geo-distributed one. In our case, we are not going to replicate Slack, we are going to use other components, but at least let's review when we will be architecting our messenger. We are going to look at several microservices. So like our application, our messenger, will be comprised of 4 microservices. The first one is the messaging one, the primary one. It allows our users to exchange messages in channels, within workspaces, across workspaces. We have the profile that keeps your data, such as email, name, age, etc., whatever you think is reasonable to share. Also, we have 2 utility microservices, reminders and the status one. With the reminders microservice, you can ask the messenger to remind about any discussion a little bit later. For instance, right now you're extremely busy, you're doing something, and you want to return to this conversation, let's say next week, and you can use a special service. You can use the reminders for that. With the status microservice, your colleagues can see what are you busy with, whether you are available or not. So generally, if you're on vacation, you can change the status to vacationing. If you are in a meeting, the status can be in a meeting. Simple. And when it comes to the architecture, we need to review and consider and talk about all the components. We are going to talk about the data layer that needs to deploy and span across multiple regions. It needs to be highly available, comply with local data residency requirements, and remain high performant, right? Then we will have the application layer. These 4 microservices need to deploy their instances across the globe so that the requests from users from Europe, Asia, and America are processed the fastest way possible. And finally, the cloud load balancer. That's a special service that is provided by major cloud vendors that captures traffic from your users and redirects the traffic, those queries, to their microservice instances and to the database instances closest to the user's location. Okay, let's move forward. Let's talk about the data layer. In our case, for the data layer, we are going to use Yugabyte DB, which is a distributed Postgres compliant SQL database. Our messaging, our corporate messenger is a transactional application. We cannot afford losing any message. We cannot allow ourselves to any inconsistencies, but we have to be global. That's why we selected Yugabyte. Yugabyte consists of 2 primary components. The first one is the pluggable query layer, and presently the query layer supports SQL. Yugabyte speaks the Postgres dialect of SQL, and also those of you who use Cassandra, you can find Cassandra APIs handy. Under the pluggable query layer, we have the storage layer. That's the layer that is different from what vanilla Postgres has. That's where your data is located. Your data will be sharded and partitioned automatically for you across your zones and regions. Your requests will be load balanced. And also all the changes, all the messages that you're going to send to your microservices will be transactional, regardless of how far the nodes of your database are located. Speaking about the compatibility level of Yugabyte DB, what it is. So generally speaking, Yugabyte DB reuses Postgres source code. Yugabyte query layer uses the rewriter, planner, executor, and optimizer of Postgres. It's basically the same Postgres, but with several components that are enhanced so that they can interact and take advantage of their underlying distributed storage layer. So for instance, we enhance the planner, executor, and optimizer so that whenever you execute your SQL queries across a GDPR cluster, the planner and optimizer can come up with the best execution plan, and the executor can send this execution plan to your distributed cluster properly. Okay, so to repeat, our geo-distributed messenger will spread across multiple regions. And this time, let's talk about the messaging and profile microservices. So those are the key microservices of our application. They are mission critical for the success of our application. They will be experiencing thousands of requests per second. They have to remain highly available even if regions go down. Because if your microservice is not available, if your messaging service is not available, then the impact and reputation and business of our company will be in danger. Also, when it comes to the data residency requirements, the messages and profile data of our users have to reside in their locations of the locations where they live. If, for instance, we have users from European region, we have to comply with the GDPR requirements, and the data of those folks have to be located in European cloud regions. So what happens? What do we do from the architectural standpoint? Those are requirements. We are going to deploy a single cluster of GDPR that spans multiple continents. But there is one important note. In this cluster, there will be a group of nodes that keep data from specific geographic locations. So a group of nodes from Europe will keep messages and profiles for the European citizens. And there will be a group of nodes who keep data and messages for their Asian customers. Which means that whenever you have, and everything will be distributed and executed for us transparently. We just need to deploy this geo-distributed cluster. The data will be partitioned based on the value of the country column. If the country column is set to UK, France, Italy, or Germany, then these messages will reside and will be kept in our European nodes. And that's done for you. We just need to configure this database, we need to create these tables, and we need to specify and say that the country is our partitioning column. When it comes to the performance, when it comes to the latency, it's obvious that if you have users from Europe and all those users work from a company that is based in Europe, all the messages and all the data will be here locally. So that whenever you insert messages, whenever you share messages or perform any other tasks, the performance will be high, the latency will be low, because the users from Europe will be interacting and reading and writing data to the European nodes of GDPR. And the same is true for North American colleagues. Let's say that you have people in North America, you need to send messages, you need to send and read and write changes from your database, you will be communicating to your North American group of nodes. Excellent. Another type of multi-region database deployment is when we deploy a primary cluster in one geographic location, and in other distant geographic locations, we configure read replicas. We are going to use this deployment mode of GDPR for the reminders microservice. Again, with the reminders microservice, we can ask the messenger to remind us about any specific conversation in an hour, next day, or any week. And generally what happens here, all the reminders, whenever someone will be creating a reminder, this write operation will be handled in the primary cluster. So if you have, let's say, a user who lives in South Korea, and this guy schedules a reminder, this reminder will be written automatically forwarded from the read replica in this location to the primary cluster in North America. But whenever you're going to read any data from these local read replicas, such as in Europe and Asia, the data will be retrieved extremely fast using the local data. And this data will be asynchronously replicated from the primary cluster to the read replicas. For instance, we are expecting batch reads. It's when in every location, close to every read replica, we will have a special worker. That's a process that wakes up every minute, connects to the database, and pulls all the reminders that have just expired. And it will be doing this only for the local data. So in Asia, we will have a special worker that will connect to the read replica, read all this data in bulk, and then will notify those users whose reminders have just expired within the last minute. Okay, so that's how you can minimize network traffic from the primary cluster to the distant locations if you need to read a lot of the data. And the third final multi-region deployment mode for our data layer, for our database, is when we are deploying multiple standalone databases in every distant location. And if necessary, we can synchronize those databases using an asynchronous protocol. In our case with our messenger, we are going to use this deployment mode for the data layer when it comes to the status microservice. Again, if you're on vacation, you want your colleagues to know about that. If you're in a meeting, also you want to change your status respectively, or if you are active and ready to chat, your status also will be set to active. And in this case, we decided, all right, we do expect that we still have, high availability, right? But we're not expecting that the status will be changed, let's say, thousands of times a second. It will happen, but it will happen not that frequently. At the same time, when my colleague opens my messenger, he wants to see statuses of all the colleagues. So like, I want to have fast reads, but when it comes to writes, I don't care. And also, asynchronous replication is suitable here. For instance, let's say that someone who lives in Europe went to a meeting and his status is changed accordingly. This information will be written to the European data center because that's where this user resides. But then this information, if necessary, can be replicated to North America and to APAC. The replication can take, let's say, like a few seconds, like 5, 10, it depends on how fast the connectivity between these clusters. But generally, it's not a big deal. Let's say if a teammate of this guy who lives in North America will see his colleague from Europe status change in 5 or 10 seconds, right? It's not a big deal. So that's why it's totally fine to use the asynchronous replication between these distant clusters. That's why we selected this for the status microservice. Okay, to conclude, that's it for the data layer component of our geo-distributed application. For this, like as I said, when it comes, there are two primary deployment modes. You have a multi-zone deployment for your data layer, or you have multi-region. Multi-zone is easy, but with multi-region, we also have 3 options. We can deploy a single geo-distributed cluster, and every data will be pinned automatically based on the value of your partitioning column, such as the country one. We use it for our mission-critical microservices, messaging, and the profile one. Also, the other deployment mode for the multi-region databases is the primary cluster with read replicas in distant location. We use that for the reminders. Keep this in your toolbox as well. And the final one, when you don't actually care about, let's say, if you allow, let's say, distant locations to read stale data that will be synchronized later, then you can use multiple standalone clusters in every location and then set up bidirectional or unidirectional replication between them. It's enough for the data layer. Let's talk about the application layer. When it comes to the application, again, we have 4 microservices: messaging, profile, reminders, and status. And we have customers across the globe. We are going to deploy an instance of every microservice in every location in North America, Europe, and Asia. Also, we are going to collocate those instances with the local gigabyte nodes. For instance, if my gigabyte DB nodes are deployed in the London data center, cloud region, then I want the instance of the microservice for the messaging and for the reminders to be located in the same region. Why so that? The latency, the performance. Remember, even if to take Google Compute Platform as an example, the latency between the availability zones within the same region is under 5 milliseconds, which is excellent. So like whenever our messaging microservice instance receives a request to write or read a message from a European customer, it will get it and it will instantaneously like request or write data to or from the database. Fast, right? It's collocated. So here is, what technology to use? How exactly do you deploy your microservice instances? It's up to you. You can use, let's say, App Engine of Google Cloud Platform or a similar service in AWS or Microsoft Azure, or you can deploy everything in Kubernetes. It's highly likely that Kubernetes containers and Kubernetes as an orchestration layer are the best option here. But anyway, we will leave this question unanswered. It's up to you, literally. Whatever is more preferable for your architecture. It's just that you need to deploy those instances across various locations. Same for the communication and the connectivity layers and patterns between your different microservices. It's true that the messaging microservice needs to read profiles from the profile microservice. The reminders microservice need to kind of pin a reminder to a specific message, and it will communicate to the messaging microservice. So here is again, I'll give you flexibility. Use a communication pattern that works best for your deployment. You can use message brokers to communicate between microservices, gRPC, like sidecar, or whatever is more applicable. Okay, data layer, application layer, and finally, we have the cloud load balancer. Because right now we have a global architecture. We have database nodes, we have microservice instances across various continents. But we want this backend and data layer to be as simple as possible for our front end, for our end users. That's why my suggestion would be to have a look and benefit from the global cloud load balancers. Usually, like every major cloud provider has them. So what's the purpose of their global load balancers? A load balancer provides you with any cast IP address that's a single external IP address that can be used by your front-end applications and your mobile applications. And when someone, let's say, connects to your front end, depending on the location of this user, the global load balancer will send this request to the closest microservice and to the closest database nodes that are located close to this user. Let's take an example. Let's say that we have a user who is based off Europe, and this user opens up your messaging application on iPhone. iPhone uses this Anycast IP address and connects to the global load balancer. The user refreshes a discussion in one of the channels, and you want to read all the messages from this channel. So the global load balancer receives this request. It sees that, okay, the request comes from a person in Europe, so then we have an instance of our microservice in Europe. Let's forward this request there. This microservice instance received this request, and it connects to it's already connected to our Geo-Distributed database, and it will send this request to our local database nodes. Easy, right? So that's how you can take advantage of the global cloud load balancers. Also, this load balancer is fault tolerant. Like basically, it supports automatic failover in case of outages. If, let's say, your data center or instance of your microservice is down here due to different zone or region level outages, the global load balancer can redirect the user's traffic to the other nearby location, to the other nearby instance. It's all done for you. Wonderful. So, at the summary, geo-distributed applications are becoming a new normal for when we are building cloud-native applications. Because usually the user base for our applications is global. Even if you're planning that your application is going to be used primarily in North America or in Asia, it's highly likely that on some day, if you become successful, then you will become the victim of your own success. You will get a global user base. And it matters a lot what was the foundation of your architecture. even if the first version of your application was deploying your messenger application and your database within a single region across multiple zones, but if it can scale to other regions and to other locations easily, then you are in a win-win situation. So right now you're using the resources that you need, but let's say in a month or like in a week you need to expand to Europe, you just span your database across, let's say, North America and Europe, or use, let's say, any other multi-region deployment mode that we discussed. So that's why think globally when you're building new cloud-native applications, and have a look and consider the different design and consideration patterns when you're building geo-distributed applications. If you want to learn more, my advice would be to check these 2 books by O'Reilly, Architecting for Scale and Designing Data-Intensive Applications. They give us more details on how to design highly available and high-performant distributed applications, and that resonates really well with the topic of today, with the geo-distributed apps. Also, if you are curious about the data layer component, about the Yuga by DB, how it works, how to deploy it, and how those multi-region deployment mode works, just my suggestion would be go and complete one of our free courses. That's the easiest way to get to know our database better. And this corporate messenger, Slack like corporate messenger, we have a Gitpod sandbox environment. Go to this GitHub project and you can run this in your Gitpod workspace. So right now we support, as of time of this recording, you would be able to start to deploy your you would be able to deploy Yuga by DB in various configuration modes for multi-region deployment, like geo-distributed, primary cluster with replica, etc. And then over the time we are planning to improve this sandbox. We're going to add the front end and the back end, etc. So you can subscribe and watch to the changes. All right. If you have any other questions, you can always find and tag me and send me a message in Twitter. Or if you are particularly interested in Yuga by DB, then join our communities like community, and you can always, the easiest way to experiment with Yuga Byte is by using our cloud product. Thanks for joining, thanks for watching, and enjoy the rest of the conference. Bye-bye.